Welcome in. You can see that our outcome for this video is to calculate density, volume, or mass using either our density formula or by utilizing dimensional analysis. We can start by defining density. This is going to be a measurement of how much mass an object has compared to its volume. This is a very useful tool. First, it will tell you whether an object sinks or floats within a liquid. Objects sink when their density is higher than the liquid around them, or they float when the density is less than the liquid around them. Second, density can be a nice, useful identification technique. As it turns out, density is intrinsic to a material. The density of a material does not change whether you have a little bit or a lot of it, and it doesn't matter where it comes from. The density of ice is ice. The density of iron is iron. That means we can collect some data and provide evidence that we do or do not have a certain material. We can point out that there is just a nice mathematical formula for density. It's going to be up here right at the top. We can measure the density by measuring an object's mass using probably a scale, and by measuring that object's volume, maybe using a ruler or some volumetric glassware or what have you. There are two main types of problems that we can see. The first is calculating the density based on some measured values. Here we go. Since the density is the mass divided by the volume, we can measure that mass and measure that volume. All that's left to do is plug in our values into our formula. When we do so, we get our answer, 10.5 grams per cubic centimeter. Our second main technique is utilizing density as a conversion factor. If we know the density of an object, for example, 1.32 grams per cubic centimeter for this liquid, well, we can phrase that as a big conversion factor like we saw in our previous video. (1.32 grams for every 1 cubic centimeter. Similarly, we can flip this upside down if we need to and get a different conversion factor. For our practice problem here, we're starting with grams. So we can use that second form of our conversion factor to convert into cubic centimeters. One last step, this problem asks for milliliters instead of cubic centimeters, but that's okay. As it turns out, 1 milliliter is the same as 1 cubic centimeter. Here we go. 51.8 milliliters is our final answer. We have two final problems. The first I'll leave as practice, but we can set up problem number 2. Here we have ethanol, and we know we want 23.5 kilograms, but we want to figure out what volume in liters that should be. We can set up a nice map. We are starting with kilograms, and we want to find liters. Notice that we know the density, so that allows us to go from grams to cubic centimeters. This is going to be in the middle of our map somewhere. Can we go from kilograms to grams? I would say yes, that's going to be a metric system conversion. From cubic centimeters to liters, well, we just did this cubic centimeters to milliliters. So maybe we can do our conversion like this. $23.5 kilograms. Let's cancel out kilograms and get to grams. 1 kilogram is big. We need 1,000 little grams to be the same. We can try to cancel out grams and go to cubic centimeters. This is our density right up here. 0.789 grams for every 1 cubic centimeter. To go from centimeters cubed to milliliters, this is a 1-to-1 ratio. That's a good one to memorize. And finally, we can go and use our metric system. A liter is big compared to milliliters. We're going to need 1,000 small milliliters to be the same as 1 liter. When we plug this in, we get 29.8. Notice here, kilograms cancels, grams cancels, cubic centimeters cancels, milliliters cancels, and liters is the only unit left behind, just as we'd like. And there you have it. We've learned how to calculate density, volume, or mass using that formula or by utilizing dimensional analysis. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.